So yesterday we saw how electronic devices like diode, they help you eat away the negative part of a sine wave and come up with only half the sine wave, which is only the positive side. And then using other electronic devices, we can convert it to a digital 1 and 0 signal. The reason we would want to convert a sine wave to a digital wave is because it is easier to store ones and zeros in computers and in memory, rather than storing a binary signal or a sine wave signal. The reason when we saw that, we ran into other problems as to how do we perform the basic arithmetic operation and other calculations. And for that, we have other format of other number systems, and those number systems, they have different radix or base of the number system. A radix is a number of unique digits. We saw that in decimal we have 10 unique digits, and then they translate to um, zeros and ones combination in binary, and they give you a set of unique number themselves. But then after we hit the upper limit of decimal, we switch to 2 digits, and that's when the sequence kind of breaks. We don't have any more pattern between the decimal and the binary number system. And to fix that issue, we have two more number systems. One is octal, which requires 3 binary digits to represent, and it has 8 unique digits. And the second is hexadecimal, which has 16 unique numbers, and they have one-to-one. Both these number systems, they have one-to-one mapping with the binary number system. Then we saw how to do the weighted calculation and figure out the magnitude of a number. Using this method, we can also convert from binary to decimal and binary to hexadecimal. Then we saw at least two arithmetic operation, add and subtract. And to do that, we um, we applied the basic arithmetic rules, and then we added those numbers. Then we studied logic gates, and then using these gates, we were able to create a machine, a small computer that is going to add two individual bits, and it's going to give us a sum and a carry. This is like the smallest, or this is the smallest computer that we can create using AND gate and XOR gate. Then we saw the subtract operation, and subtract is kind of an addition if we can find out the difference between the number and the radix of that number system. And then when we add, there are rules that we have to apply because of the carry, and then with the carry you would know if the result is positive or negative. In the binary world, in the digital world, it is done using ones complement and two's complement. Ones complement is flip all the bits, two's complement is ones complement and then plus one. Then we found out that there is a unit which is called ALU, and an ALU has multiple adders and subtractors in it. This ALU becomes part of the processor, and we saw one processor a little briefly, which is 8086, and 8086 has option to take input from devices. It has options to store, connect to a RAM, and then extract or persist information there. Then we saw how a small looking C program, English Readable High Level Language Program, gets translated to microprocessor language and the binary language. For generating this binary language, we saw the 8086 mnemonic code chart, and then these charts helped us translate this C program or this high level language program into a series of bits and bytes. And then we saw how this structure is going to get laid out in the memory. There are going to be multiple sections, one for code, one for data, one for stack, and one for the access segment. And then 8086 CPU internally has pointers to the beginning of all these segments in the memory using these segment registers. Then some segment registers, they also have a pointing register, which is say SI and DI. And then for code, there is a special register called IP. The unique combination of CS and IP is going to change the flow of your execution. You change the value of CS and IP, and then the instruction sitting at this combination, CS colon IP, is going to get executed. When we call a function, what we actually do is we influence the value of CS and IP, and that's how the call instruction is executed. This is the same for the jump instruction and the goto instruction. When you put a goto instruction here, the value of CS and IP is going to get influenced. The call function is special because call function is going to save the value of the next instruction after the call statement into a special place called the stack, and that is pointed using the stack segment register, right? And then when we are inside that function, we are going to run into another statement which is called return, and then return is going to say that we are done with this function here, and we would want to go back to the address that you had saved in the stack. So it is going to come back and restore the code segment and instruction pointer, and then the flow of our execution in mnemonic code is going to jump here. And if we are writing, say, some higher level program like this one here, the add function, the next statement after add is going to come back. So deep inside the processor, it is these segment registers that are getting modified. All right, moving on. Those programs, 8086, it was succumbed to interruptions and malicious code because of the structure of the code, because it can have pockets, and in these pockets, if we make the code jump to other part of memory, we can uh, generate viruses or malicious programs. 80386 was a little mature processor, and it can tag special segments of RAM with special permissions. So if you give it a permission of execution, it is only execute. If you give it permission of data, it is only going to save the data part of it. So these are some of the processor internals that we saw yesterday. Now, the reason we saw this is because there are multiple core level concepts that are related to the C# language. So let's go ahead and get started with the C# programming itself. Now, right, so we saw that there are like multiple programming languages. One is the binary language, which is the machine language itself, right, which is series of bytes, very cryptic. Above that, there is a mnemonic language, which is instructions like move and call and add and jump. Um, these languages, they are difficult to program, and then they don't give us a sense of control. So above this, we started creating high-level languages. Now I'm speaking at a very rough level. There is definitely more to it than meets the eye. The high-level languages, the objective of these languages is to create programming in a way that the reader of the application should be able to understand what is the intent, or okay, so what is the intent of an application and what somebody is trying to express through these coding statements. So if I write a code like this, right, it is probably doing addition of two numbers, and it is saving the result in a variable called result. Now, the reason this is human understandable, this is human readable, but eventually this has to get converted to the platform that you are running on. So if I can draw a diagram around it, this is say C, C++, or C# code. This code has to get converted into an executable. Now, this executable is going to have multiple sections in it, and then these sections, they are going to represent, some of these are going to represent how to store these variables. Give me 1 second. Right, so let me go ahead and just start typing. So the exe is going to have instructions that is going to show a way of storing these variables, and it is going to have separate set of addresses, like it's going to store the variable I in a location called ff. It is going to store variable j right next to it, probably on 2 bytes away. on location 102, and then these instructions they become part of the exe. But then when these exe they get loaded in RAM, or they are supposed to be executed, there are multiple things that should happen in the code, in the CS and IP register value, and in these register value they are going to control the flow of the execution. When this transition happens, it is not just these statements that get translated and become part of the exe. Inside an exe, you are also going to have a lot of instructions for, say, the operating system. So the OS is going to know that where the code actually begins. So if the code begins at, say, address 100, there will be special instruction inside these exes, which is going to tell that this is the beginning of code. Suppose if your application has some data requirement, that is going to get mentioned here as well. If you have, if there is a special place where the stack is going to begin, that information is also going to become part of it. If there are other DLLs, so DLL is another part of an application. So this is going to say have additional operation like the math DLL that you have. It is going to have the add and subtract and functions like that. And then your program might want to work with, might want to reference some of the code that is present in another file altogether. So this is your main.exe, this is your math.dll. If you want to include a file like this in an executable, you would want to provide some form of linking between the exe and the DLL. And in that code, it also has to be specified in some way as to what DLLs you will be requiring. And then eventually it is the operating system that picks up this file, it figures out all this information, and it loads this thing into the RAM that we saw very closely yesterday. Now what happens is when you have an operating system and a microprocessor, each microprocessor is going to have a different set of instruction. Like 8085 had very limited move instruction, but then the move instruction in 8086 they were significantly increased. In 80386, in the multiple Intel processor, there are significant hardware level changes. And then as you switch from operating system to operating system, you will have to also change the way these executables they are created, because each OS is going to have its own mechanism of loading these binary numbers and making sense out of this data before it can be executed on the processor. So the trick for that is that you create an extra layer of indirection. And in this layer of indirection is going to isolate what operating system you have and what microprocessor or what processor you are going to execute this code on. So initially when people were writing code back in the 60s and 70s, their biggest concern was to identify which processor this code is going to run on, and based on the processor they're going to have different compilers which is going to convert this English like code into a more machine understandable language. All right. And when programming and when there were like multiple processors, languages like C Sharp, they started coming up with frameworks that is going to abstract out the operating system with more modern version of .NET. And earlier, it was platform agnostic, so it won't care which platform it is running on, as long as this code is, uh, as long as this code compiles in the C Sharp compiler. So what they did is they created based on based on the operating system that you are running on, they created different layer of program which is called the CLR, which is more like a runtime library. And this library is going to convert the C Sharp code into a language that the .NET framework or the CLR understands, and then that language is called an intermediate language. Now, this intermediate language can be taken up, and depending on if you are on Windows or Linux or Mac, it is going to get converted to an exe or probably a code that can execute. in Linux and Mac. So what they're going to change is the next abstraction from here, which converts the intermediate language code into one of these formats, and you're going to have different versions of compilers for different platforms. So let's go ahead and see an example of that. I'm going to fire up Visual Studio. Right, for now, I'm going to create a console application. Just going to call it Hello C Sharp. And don't worry about if it is .NET Core and you don't know .NET Core at the moment, but I'm just going to run it for 3.1. Right, and over here I'm going to say integer I assigned to 10, integer j assigned to 20, and integer result assigned to I plus j. That's it. And when I click on the run button, it brings this output back. And because we are not printing anything, I mean the code is just going to run, it's just going to exit out. But my objective for seeing this, let me just go ahead and put that line. Let me run it again. And then we saw 30, which is the value of result. So let's go ahead and try to analyze this program. So this program starts with using a statement called using. This is where the system level functionality is going to come in, and functions like console.writeLine, they are going to get supported. We did not write this code. It is present in using in the system assembly. And this is what I meant by including other people's code inside our application through specific DLLs. Now, there is something called a namespace. It is a segregation boundary. When you're working on a complex application, to have a boundary, a logical boundary between different classes and different functions, you are going to put them inside a specific namespace. A namespace is just a containing body which is going to isolate this main program from, say, there is another namespace, and that namespace can have a class named program because they are in different namespaces. So look at this as an isolation boundary, something that separates classes from other people's, other DLL's code. This is the beginning of a function. We're going to look at static more closely in the next few sessions. The function name is main. It accepts a few parameters, and then we are declaring two variables, integer I and j, and we are storing the sum of addition of these two numbers in a variable called result, and we are just printing on screen. So a technical name for such screen is console, and writeLine is going to write a line, and then we are just passing it the value of result, and it's going to get printed. But I did not want to show you, I mean, this was like one objective, but then there was more that I wanted to show you. There is a utility called ILSpy, and I wanted to show that to you. So if I right click on this and open it in File Explorer, I'll notice that this is our program file. The project that we created itself is saved as the CS_proj file. We're going to look at the CS_proj file very shortly. And then there are two folders that it generates. So bin has a folder called debug, and debug has a folder for the framework. Because we selected .NET Core 3.1 while we were creating the solution, it created 3.1 folder, and notice that it has multiple DLL files, an exe file, and a PDB file. We're going to talk about this probably sometime in the future as well. I have launched a special program, and that program is called ILSpy. Right? As a .NET developer, everyone, I would highly recommend that you install this particular software on your computer. Now, what I'm going to do is I'm going to drag this DLL file into ILSpy. I'm going to just drop it here. And then notice that it has kind of tucked itself into this Explorer window. And then this is the namespace that we saw inside our code. So if I can do back and forth between C# and ILSpy, you're going to see that namespace is hello C#, and that also happens to be the enclosing body for this particular assembly. Right? If I click on this plus sign here, it is showing that it has a class, and notice that as we are drilling down into this, there are different icons that are coming. These icons, they should start making sense to you by now, that this is for namespace and program is for class. When I click on the plus sign, notice that there is something called as base type, there is something called as a derived types, there is a program, and there is main function. So this program here is probably for the static object that we have. Alright, so this is the constructor of it. Constructor is something that we're going to see when we talk about classes more closely, but then this cube here represents the constructor. And then if you look at this, notice that there's a little lock icon here, and there's an asterisk sign here, and then it's a blue cube here. Alright, this lock here indicates private, which is an access modifier. We're going to see that as well. And then this asterisk here indicates the static keyword. And then it is the same program that we typed, coded into the Visual Studio as well. So ILSpy is going to open up your DLL, and from the DLL, it is going to generate your project code back. Alright, so this is functionality number one. Number two, this little drop down here is going to show you what the C# code looks like, what the intermediate language code looks like, and it is going to show a combination of those two. So let's look at the combination first. Right, and notice that there is something called as dot entry point. Right, there's something called as max stack. There's something called as dot locals, and the locals is declaring all the local variables that we have. Right, and in the comment, right, so everything that is C# is commented by these green lines, and then everything that is part of the intermediate language, it starts with IL, and it looks a little cryptic. But then notice that it is saying that IL00, there is a command called no-op. No-op is short for no operation. And then it is doing some move-like instruction, and then it is moving 10 somewhere, right? And then I think it is the stored location, which is 00, and then probably it is pointing to the variable I. And then notice that it is integer num. So it has also gone ahead and it has replaced variables like I and j and result with terminology of its own. So it is integer num assigned to 10, but then that is not what we had written in our code. Right? Integer num2 assigned to 20. We definitely had a j here, and then it was definitely not value, it was a result, and we were doing I plus j. So the IL, the intermediate language, has gone ahead. All right, I'll put the sentence the other way. So the C# compiler has gone ahead and it started reading these things, and then it started converting it into a different language, which is called the intermediate language. And the intermediate language is replacing our variable names with names specific to IL, and it is replacing our instructions as well. When we do the sum instruction, we are seeing that it is trying to access location 0 and location 1, which is these two variables here. It is doing the add instruction, and it is saying that store it in location number 2, which is the result instruction. Right? And when that happens, there is a call instruction, which is calling. Okay, look at these square brackets. It actually indicates probably a namespace and a different assembly, and it is with these double colons, it is separating out the class with the function name, and it is also indicating which data type we would want to include, and it is saying integer 32. We're going to see a different example where we're going to see a string over here, and when all that happens, it inserts a no-op instruction, and the no-op instruction probably is inserted so that it can better align a couple of other instructions. And the last instruction is a return statement. But then our code did not have a return statement. So we're going to see an example of this as well very, very shortly. But then the point that we were trying to make is that a simple, innocent looking program, it gets converted into a little cryptic code which has one-to-one equivalence. It's still understandable. And then from this, it changes to a series of ones and zeros through another round of execution. Now, the reason .NET does that is because it wants this code to be executable on any platform and any processor, right? So this is like the intermediate part, and after this, it is going to be platform and operating system specific. So depending on what platform you are running on, it is going to give you a different exe. But then all the programs on all the platform, they're going to spit out the same code. They're all going to spit out the same code, and it is through this code that we will eventually have this exe, or the exe that we saw in the digital electronics section from yesterday. So with this understood, let's play around with this file. Now we know that how integers are converted by IL. I'm going to switch to an easier program, and we are simply going to write hello world over here. I'm going to hit save, and when I'm not going to click around, I'm going to hit Control F5 this time, and then it gave me this output. So anything that I write in the console.writeLine statement, it is going to get printed on the screen here like this. Now, if we go back, we might have to refresh this code, and there's this little refresh button. So once we do that and start drilling down again to the main function, notice that this time WriteLine is not taking integer 32, it is taking a string variable. All the other noise that we had, that has also disappeared. Now, I should have told this earlier, but an entry point and then max tag is indicating this little section here that goes and as an instruction to the operating system as to how we would want our assembly to get loaded. Where does the code start? So there was something called a dot entry point. So the code actually starts here. Where does the data start? Probably somewhere over here. And then it knows how to access, because we don't have any data, we have removed that section. But where does the stack begin? It says that the stack size is 8. And I'm going to give you better examples of this, but then this stack size is coming because we have this little argument here. So let's go ahead and remove this string arguments, save it. I'm going to hit Control Shift Build. I've just built it because I don't really want to run it this time. If I refresh it again and look at this, our program, the main function, right? I don't know why this is coming. Let me try another statement. I don't know if it is even going to work, but then back in the C programming days, I used to write a void function here, and then probably C# does not support it. When you put a void here, you are specifically telling the compiler, at least in the C programming, that you are not expecting any parameters, right? It does not allow me that. So I'm going to delete it, and we're going to say that at least it is going to require a stack of 8 bytes. It runs the rest of the code, and then notice how the string constant is declared as LDSTR. So it is a string that it has defined, and it is going to figure out how to pass this value to this particular function. But then the value itself has been pulled out, and it has been broken down into 2 separate instructions. I wanted to show you one more thing. So if I declare a variable here called, I'll have to declare a function. Let's see an example of function. I'm going to call the function name as add. I'm going to delete this. And then because we have static here, I'll have to make the add function static as well. So let's change this to add, and then I'm going to type integer x and integer y. And I'm going to return x plus y. And I've built the solution, Control Shift and B, and let's reload this part. So notice that as soon as we added 2 functions, the add function started appearing here in this assembly. Now look at this, that it has created once again 2 variables, and then this time it did not create any more variables because the compiler was smart enough to identify that these variables, they are hard-coded values. They're not going to get modified, so it did not declare num and num2 like in the previous case, and it um, save them as hard-coded strings, and notice that the function call once again is separated by two colons, and then there is another call instruction, and then there's a pop instruction. So the call instruction is going to transfer the control from the main function into the add function, and the add function here has its own stack. So notice that it has a stack size of 2, a different stack size because of the different variables that we are accepting here. And then it is declaring a local variable and it is initializing it to a 0. This value is going to get used inside the return statement. So with this, the add function, it has translated the x plus y statement into multiple statements. So it took variable 1, variable 2, it added the add statement, and then it saved the result somewhere. It is the store location 0, which is this value here. And then it said that it is no C# code. I don't understand what this means. Let's have a look at it. Okay, I have no clue what this is doing, but when I clicked on it, it popped open a browser window for me, and it is saying that unconditionally transfer control to a target instruction. All right, and then probably if I try to decipher name, it is a short form of transferring control. So BR probably is short for branch, and S is short for short. So it's a short branch, and it is jumping from in the same DLL file. So because they are part of the same DLL file, it's a short jump, and the short jump is saying that you would want to jump to instruction number IL007. Now, if I go back to the main function, you're going to see that IL007 is probably something next to it. So we were all the way up to IL005 here, and then 7 is somewhere in between these two, and it is going to, next instruction that it's going to do is pop, because this pop is going to set the stack correctly again. But let's just ignore that, and then let's look at this branch statement. And then this branch is going to translate in the exe to the return statement. And okay, probably it is not main function. I'm so sorry. It is probably jumping right here. So branch is an unconditional jump. It is going to jump to IL007, which is this line here, which is this line over here, and then it is going to execute a return statement. And then over here, I don't know what this LD location 0 means. Alright, so I've clicked on it, and once again it popped up in this browser window. And in this browser window is saying that it is load the local variable at index 0 onto the evaluation stack. In English, it is saying that the return statement that we have here is going to save this result of the sum in a specific location, and we are trying to save that instruction. We are trying to load that instruction, which is the evaluation result, and then that evaluation result inside our stack is available in this location. So LD location 0 is actually this local variable location 0, which is also an integer, and then when we execute return, this return is going to get assigned. If we had declared a variable here like integer result, it is going to come and get stored in this value, and then once again with console.writeLine, it is going to get printed on the screen. So if I just compile this code and refresh our intermediate language examiner, ILSpy, notice that it declared another local, which is saved as a result. From this point onwards, it's going to have a different value. But then over here, we call the add function. The add function came back, and then it started saving something to a local variable, store location at 0, and this is where the result is going to get stored. It is going to load that value, and then it is going to print that value through this call statement. All right. So a simple looking C# program is going to run through the compiler, and it is going to get translated into an intermediate language, and through that intermediate language across different platform, it is going to generate different executable files. So I hope we have covered all the scenarios where we are accepting parameters, where we are not accepting parameters, where we are calling functions, and we are modifying small variables, right? So we have declared a few variables with the integer keyword. If we have to talk about the data types that are available in the C# programming language, I am pretty sure that you know all the basic ones. There's something called as integer. There is a boolean for storing true and false. Integer is for storing integer values. And then we have char, which is for storing a single character. Then for floating point, we have multiple data types: float and decimal. And right, for long integers, we have another data type called long. Let me see if I'm missing anything.
Double, sir.
Right, there's a double for float, and then double sits here. Right. So these are primitive native data types. There are multiple variants of these data types as well. So integer, if I hit F12 on it, it is going to take me to a different class. Alright, notice that this is integer 32, and what we have typed here is int. So int is an alias, or is a short for integer 32. So if you write integer 32 or you write int integer, it doesn't make a difference. But then let's look at this class more closely. What it is saying is that it has a maximum value of around 2 GB, and it has a negative minimum value of negative 2 GBs, 2 giga, not bytes, right? And it has multiple other operations. What I want to bring your attention to is this inheritance hierarchy, and notice that it is getting inherited from multiple interface-like statements. We're going to look at this more closely, but then what I wanted to showcase was that this integer is going to store positive and negative numbers both. There are other variants of integer, which is unsigned integer, uint, and if I hit F12 on this, it is going to jump to its definition, and it is uint32, and it is starting all the way from 4 giga to a 0. So that is the range of that variable. Now you can explore all these variable types, and I mean they'll tell you more of the internal implementation of what each of these data types are. After these data types, there are other derived data types, which are combination of these basic data types. So if I so an array is a derived data type, which is derived from the native data type of integer, and it requires a syntax of a square bracket next to it. So once you put a square bracket, it is saying that I'm not going to store a single value. I am going to store a series of numbers, which is 1, 2, 3, 4, and 5. So instead of storing like one single variable, you're going to store 5 variables inside them. You can store multiple variables inside them because you did not specify the count over here. So if I say 10, it is going to assume that the next values are not specified, and then probably it is not going to sit over here. I will have to specify it inside this section. So if I want to initialize it, I'll have to put 10 on the right hand side and not on the left hand side. So this is saying that nums is an integer array, it's going to have more than one value, and then this new keyword here is going to initialize with this particular count. This count here is optional. If you don't want to specify it, that is fine. And if you delete all of this, that is also fine, because C# compiler is smart enough to figure out that this is because it is integer and square bracket, the values here should be integers, and then if you try to put a character here, it is going to give an error right at this spot that this is a little cryptic way of saying that this does not look like the integer data type. So we're going to delete that. Alright, so that is the basic of data types. I don't really want to explain you what integers, characters, and floats are. I would point you to Microsoft documentation, and then you can read more about there, or probably you would already be knowing that. What I wanted to talk about was there are two type of variables inside C#. One is a value type, and one is a reference type. So let's jump back to whiteboarding, and I'm going to type. So we are talking about data types. We saw that there are some native data types like integer and character and so on, right? But then these data types, they are broadly classified into two categories. One is a value type and the second is a reference type. Now, if you remember our discussion from yesterday, uh, why we looked at microprocessors and memory so closely, because this distinction is now going to start to make sense to you. A value type is something that gets stored right there in the stack. So the stack segment ss:IP register, it is going to point to this particular variable here, and then if I say integer I and assign it a value 10, it is only going to be limited to the scope of the function. So if I declare it inside main function, only the main function will have access to this, that is number one, but then any modification that happens to I will only happen inside the main function. We saw another function called add, and if I pass this value of I inside this function here and change it to say 20, when this function returns back, when this function returns, this memory location inside main function is still going to be 10, and those are in very short value types. So let's go ahead and declare a variable integer I assigned to 10, and then if I put the add function and define the static void add function integer, I'm going to use the same names, and then I assign 20 to this. Right now, if I print the value of variable I, right, because it's a value type, it is going to print 10 and it is not going to get modified. Right, so it is still printing 10. If we put the print line statement here and hit Control F5, it is going to print 10 twice, one before calling add, one after calling add, and then I can put other logging statements inside these functions just to make a point that I was 24 when it was within the function, right? So 10 is in the main function, 20 is in the add function, and 10 once again is in the main function. The point being that native primitive data types, they are value type and they don't get modified. Their scope is restricted to the block that they are declared in, and when they are passed to different functions, the different function is going to have its own local copy, and they are going to work on their local copy. And when we return to the calling function, we are not going to change the scope of that is not going to get affected. But it is a little different when it is about arrays. So I'm going to type nums here, and let's change this value to 1, 2, 3, 4, and 5. And over here, I'm not going to try to print now. I'm not going to do this. Let me combine it with another programming construct, which is the for loop and the for each loop. And I'm going to say that from nums, take one item at a time and just print it for me. So let's just see what these items are going to do. And if I hit control, okay, let me fix that real quick. And if I hit control F5 now, alright, it is printing 1, 2, 3, 4, 5, like one value at a time, and the for loop is going to get executed for each element inside nums, and it is going to print the value. Now let's just go ahead and accept this over here, and I can access this nums using the index operator. So the indexing for arrays start with 0. So number 1 is at index 0, index 1, 2, 3, 4. Let's try and modify the value 3, and value 3 is present at index number 2. And if I assign 20 to it and type nums of 2, it should print 20 here. And then when we come back, I'll also have to call the add function. So I'm going to call the add function, and I'm going to pass it nums like this, and I'm going to repeat this section. Right, and now if I run it, right, it has printed 1 2 3 4 5. So before we called it, inside the add function it said that the value has been modified, but when we returned, nums printed number 20 for this value here, which indicates that this value that we have passed to nums, it was the same value that was received in the add function. It was exactly this collection, and then this collection is getting modified inside this function, and it is the modified copy that we are accessing once we are on this particular line. Now probably I should have shown this to you in the IELTS file as well, but then once again let's go back and look at the assembly intermediate language code that it has generated. So the main function is a little complicated now. It has a lot of variables here. It is declaring integer 32 nums and a couple of other variables. It is going to reference that with SD colon 0 or LD colon 0, something like that. So ST location 0 and things that ways. And it has special ways of identifying loop. So the for each block has been converted into this particular section here, and then it is calling it loop. And inside this loop, it is accessing some variables, and then eventually it is calling a write line, and it is printing this value over here. So this is the for loop inside the assembly language. And what I wanted to see was the call for the add function, which is over here, and it is saying that LD colon 0, which is the first variable, this collection over here, it is getting passed to the add function. And the add function is going to access the same memory location, and then it is going to modify, it's going to assign value 20 to this thing, and then it is going to call the write line function over here like this. Now so notice, I mean, how as we are writing more and more complex programs, I mean, these statements, they are getting added here, and there are new keywords that we are seeing. And I was trying to make a connection between this variable here nums and then this variable over here. But we saw that it was the same member location that got passed, and it was the same memory that was assigned. So if we jump back to our whiteboard, I'm going to open up the digital electronics section from yesterday and probably give you some more detail about how this thing is working internally. So what we had so far was this. I told you that the exe that is getting created, the series of bits and bytes, it is sitting in this code section. And then there are two types of data segments that we have. One is the data segment, where we are going to get some memory from the operating system, from the program. And then there is another section which is called stack. When you are inside stack, it is this space of memory that you are using, and the local variables like I and j, they are getting saved here. So if I can label these sections, I'm going to say that value types, they have a house over here. So when we saw that previous example where I was getting passed to the add function and was not getting modified, is because in the stack, by the way, all the functions, they share the same stack. So integer I was sitting here. When integer I was run, over here we had the return value of CS and IP from the main function, and when we were inside the add function, the variable I that was inside add, it was sitting over here, right? So this copy of I was for main, and then this copy of I was for function add. When we assigned multiple add statements, it was this combination of stack segment and stack index that we were accessing. And because both functions, they were accessing different copy inside the stack, the effect was not getting changing the value of I inside here is not affecting this value because obviously they are two separate values. But when we moved to the reference section, when we changed integer to integer array, we started referring that integer array of numbers from this particular section, right? So all that happened is because it was a reference type, the main function did not declare this value type. It was like, okay, because you are a reference type, I'm not going to give you a space in my stack. I'm only going to give you space inside this data segment here, right? It is this data segment that is getting modified, and when the add function got called, add function received it as a reference type as well. And then it started saying that, hey, you have passed me a reference, which means that you have passed me something from this part of RAM. So I am also going to deal with this, and I'm not going to declare my own variable. So all that was there on stack was that return address of the add function in the main function, right? So it saved the CS and IP of this statement here. It's something down below over here. It saved CS and IP of this inside this tag segment, and I started modifying that number. And that's why when we modified this specific number over here to 20, it said that because we were all working on the same copy of data, I'm going to go ahead and modify that copy that you gave me. And then it is through this that we saw that after returning from the add function, the num's index number 2, it changed from 3 to 20. So deep inside, this is what happened at the processor level, and the assembly language or the intermediate language code is going to be in sync with that as well. So the add function is going to receive, let's go ahead and look at the add function. So we declared an array here, we initialized the array, we printed the value of array, and then we called the add function. So the add function is called over here, and it is referring to this particular variable, and then it is saying LD location 0. I think so far we were seeing ST location, which is for a short location, right? And then LD probably is something that's going to have a long index, and then it is that long index that we have passed to the add function. And then add function started modifying that variable using these statements. So it is load argument, and then it did some more calculation before it assigned the value to it. So the add function is actually referring, going back to this particular section, it is calculating that address, and then it is through this address that the memory location is getting modified. All right, so these are value types and reference type. Let me jump back to our C# whiteboard. So value types, they are going to get declared on the stack. Each function is going to have its own copy, and reference types, they are going to get deployed on the data segment inside RAM. Right? There are advanced C# concepts that we are going to discuss, and then that's when this data segment is going to start making more sense to you. But then for now, understand that it is the stack where these values were getting stored. All right, let's take a quick break. It is almost 9 at the clock. We're going to come back at 9:10. And when we come back, we are going to look at other data types that are available in C# language. Right?
Yes.
Thank you. So before we went on a break, we looked at um, what machine level code is, what mnemonic code is, what high level code is. High level code reads more like English, and using compilers, we convert this high level code into a machine level code. which is a series of bytes that is going to do a special work for that specific processor. But then, as there were more processors and more operating system, things started becoming very complicated, and then that's when frameworks like C Sharp they jumped in the picture, and then they started adding extra layers of indirection, and these indirections they are going to convert the English like code into an operating system specific and then a platform specific code. Then we saw the role of IL and how IL is converting this into an intermediate language. Then we looked at some basic data types and how value types are different than reference type. Value types, they go and sit on the stack, and each function is going to get its own copy. And because they are working on their copy, the changes are not going to get reflected in the other category, or I'm so sorry, in the other function. The reference type is declared in the data segment of RAM, roughly speaking, and through this data segment, all the functions they are going to access the same copy, and because it is the same copy, the changes are going to be persisted across or reflected across function calls. I would highly discourage doing that, and as we make progress on our course, we are going to devise ways and better techniques around that. But then let's look at data types more closely, and I'm going to jump back to our C sharp program, and over here I'm going to get rid of this code. I'm going to say integer I is assigned to 10. Now, on this integer, I can perform multiple operations like 10 plus 2. Right? I can probably duplicate this line with Control D. Right, so probably right. I can perform another operation over here on a new variable and perform subtraction. Right? I have all the other options of multiplication, division, modulus. So integer supports all these operations, and then we know that when we perform what result to expect when we perform these operations. But then if I declare a character variable, call it x and assign it a value of capital X, right? If I say x plus 10, and what is this output going to be? Let's go ahead and assign it to a different variable. I am habitual to writing var keyword over there. I'm going to explain that probably in some future section. But then notice that when we saw the JavaScript sessions, we saw that even if you put 10 here, JavaScript goes ahead and appends 10 in front of this and assign it to the value on the left. But then C Sharp is complaining about that and is saying that cannot implicitly convert integer to character. But it is essentially saying that I cannot, I this does not look like a character, and then I can only perform addition on character. But then that is not going to change anything. Let me call this y, and now that I'm going to change this value to z, and it is still complaining. I think that cannot implicitly convert integer to character, right? So the error message has just changed, and then all we are trying to do is we are trying to probably concat these two or probably add the value of these two, and it is not working. The point that I'm trying to make is that a data type is two things. One is the data that it can store. It can store integers, and two, it can store probably character. So depending on what you define on the left side, if you call it integer, it is going to store integer values. If you define character, it is going to store character values. So that is part number one, the data that it can store. And part number two is the operations that it supports. So an integer is going to support addition, multiplication, or the arithmetic operation. A character is going to support operations that can be performed on character. Right? With this knowledge, if we come back and probably try to draw it out on a whiteboard, an integer to me is going to look like this, that it is a series that can hold from -2 giga to +2 giga, and an unsigned integer is going to save from 0 to 4 giga, and then a character, because it is single byte, it is going to save something from say 0 to 255, right? Only those many unique combinations. So this is like the first part of it, which is about data storage or data representation, as to how those things are going to look in memory When I say that integer is unsigned and it is saving -2 to +2, this value here is going to act as a sign bit. It is either going to represent the plus sign or the minus sign. But then when I say that it is the unsigned integer, the structure of the data did not change. I mean, we still have those 32 bits that are available to us. But then I'm saying that I'm going to change the representation of this value here, and I'm not going to treat it as a signed bit because I know this is an unsigned integer. So everything is positive, right? So it starts from 0 and goes all the way up to 4 gigabytes. So the range is same, the value is same. It is just the interpretation of the data based on the data type that we have defined. Make sense? Character is a lot smaller, and for character, sign bit doesn't make sense. I'm not going to say that plus a or minus a, right? Character is a character, and in all 8 bits, they are going to represent some value. With that said, I'm going to give you another concept here, and it is called ASCII, American Standard Code for Information Exchange. I'm forgetting what this stands for, but in ASCII codes, they represent that each combination of ones and zeros that we save here, they are going to have a special meaning. So the character A is actually 65, and if you translate this to hexadecimal, it is going to be 41. Try to remember this value, and then small a is 97, and in hexadecimal it is 61, and then for hexadecimal I should actually put 0x, so it is 0x41 and 0x61. uh, what it essentially is saying is that for a the combination is 1010, and for 1 combination is 0001. So when I see these 8 bits and this is the character type, I'm going to treat it as capital A. Right now we know that in the ALU we have something called as binary adder using the AND gate and the XOR gate. But then if I can perform add operation on these series of bits, why can't I add 2 characters? Because higher level language, they restrict the operation to the data type that you're defining. Anything that is available to you from the processor level, it is kind of abstracted. And the reason we do that is because the code that we are writing here, we want it to be human understandable. We are not dealing at machine level, we are dealing at human level. And when we are doing that, we would want to perform operations that makes intuitive sense to the reader of the application. With that said, we covered the first part as to what the character in memory looks like, what the integer looks like, what unsigned integer looks like. Along with this comes the second part of the operation, right? On integers, we perform plus, minus, divide, multiply, and probably modulus operation. On character, we can only probably change it to a lowercase or probably to an uppercase, right? So that makes sense. I mean, if I have A, capital A, I can change it to a small a by changing 41 to 61. And then let me write those two values here. So 4 in binary is 0100, and then 1 is 0001, and da, 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 97 is actually 61, and 6 is 0110, and then it is 0001. Okay, so this is capital A, this is capital A, this is small a, and then the only difference between these two characters is this bit number 6. Bit 0, 1, 2, 3, 4, 5 is bit number 5, right? If I can flip bit number 5 from 0 to 1, I get the capital letter. And this is where you see the potential of hexadecimal number system. I picked up a code, I converted it to binary, and I saw the difference right away. With decimal, it is kind of difficult, right? And the difference between these two is 32, right? And then if you calculate the value of 32, it comes out to be 2 is to 5. So when we call the function to lower, what happens at the ALU level is that it is going to go and flip bit number 5 from 0 to 1, right? And then we have it. If I want to go to upper, right, to upper is going to change this 1 to a 0, and then it is going to become capital A, or the capital equivalent of that. Make sense? It'll have to perform some checks that it is the to lower function is between A to Z and it is between A to Z. Once that series is verified, all you have to do is just flip bit number 5. Make sense? Now, using this, we can also do a kind of comparison. So we compare characters all the time. Like when you are building an application that is going to compare your super complex password with this new password that you have entered, the way you're going to compare is you're going to check all these bit operations, right? So the first bit is matching second, third, fourth, fifth, sixth is flipped. Sorry, okay. So bit number 5 is flipped, which changes capital letter and small letter. We're going to talk about that, but then the other bits are all matching except bit number 5, right? If bit number 5 does not match, probably the case is not matching. We can say that the numbers are not matching either. But there are two type of comparison that you can do. So compare, you can pass it an argument and you can tell it that I want case sensitive or case insensitive. And when you do that case insensitive, you would want to ignore the result of this. Okay, I'm going to show you something more. Uh, when these two are equal, I want the output of 0, right? When these two are equal, the output should be 0, 0, 0, 0. And because these two are not equal, it is going to be 1, it is going to be 0 and 0 again. Ignore this bit, but then tell me the gate that we are going to use if we want to compare two bits and get an output 0 if the value matches. It is the XOR gate, right? So if I, in the ALU, if I put together 8 XOR gates, and if I pass all these values over here on each line, the output that I'm going to get is a series of zeros, right? And only for this particular bit, when somebody says that ignore this particular bit number 5 and do case insensitive comparison, I'm going to say that for bit number 5, I'm going to create another series of 8 XOR gate, but then for the fifth gate, I'm also going to add a NOT gate. All right. If you look at the mnemonic code of this at the 8086 level, it is called the compare instruction, and in higher processor, there is another instruction called compare I. Compare I is going to select this NOT gate implementation. Compare instruction is going to select these 8 XOR gate implementation, and it is going to do case sensitive comparison. So the character.toCompare in the exe is going to translate to this compare instruction, and compare with ignore case is going to translate to this compare instruction. Compare insensitive is going to pick up the NOT gate. So as you are writing these programs, you have to be aware as to what is the processor going to do inside. I mean, that knowledge is definitely going to improve the quality of your program. So uh, each data type is going to tell you about the storage, and with the storage, it is also going to tell you the operations that are supported. So multiplication to lower to upper, compare, these are the operations that we can perform on characters. With that said, these native data types, they are not enough, right? And probably a scenario is I want to store the student information. Now, student is going to have first name, student is going to probably also have a last name, and they're also going to have marks on multiple subjects, which is an integer array. When you see that the native data types, the primitive data types available from the language, they are not enough for getting a job done, you switch to uh, a new concept to a different way of creating data types, and it is called as abstract data type. An abstract data type is a combination of multiple primitive data types. What are primitive data types? Integer, string, boolean, float, whatever. When I have to define a student, I create an abstract data type, and I say that in a student, I want to save the first name, last name, its marks, its history, stuff like that. With that, we are only solving this problem here. Integer were like pretty straightforward. They were 32 bits. Character were like even easier. They were like 8 bits. But then abstract data types, they are a little complex. They are string data type, and they're going to store multiple series of characters. They are integer arrays. They're going to store multiple values of integer. Right? So we have only solved the first problem. We have, by putting these all primitive data types together, we have told the processor or the program how we would want to represent our newly created data type, and that's why it is called abstract data type. right? We are just laying out the structure of that particular thing in the memory. And we are doing that by what is available to us from the framework itself. But the second important piece of a data type, as we have seen before, is operations, right? Do you want to add two students? Doesn't make sense. Do you want to convert the student to lowercase? Doesn't make sense. There are specific operations that you would want to perform on the student itself, and that operation could be update first name, right? That operation could be calculate result, right? So when we do that, what we are actually laying our foundation for is called classes. When you are putting together multiple primitive data types and you are also defining the operations that they can perform, you have essentially created a new data type, which is called an abstract data type. And depending on what you name it, you have the flexibility of naming that type as well. You can come up with anything like a student, a bank account, an employee, an organization, probably a sale, probably a tweet, right? If you are probably creating Twitter, right? What we are going to do is we're going to put together multiple primitive data type and come up with a new data type with the set of operations that are defined inside them. With that, I'm going to pull up a problem statement from the internet, and I'm just going to paste it here. So I'm going to say add paste. Alright, so it is saying that it has 10-digit number that uniquely identifies the bank account. It has a string that stores the name or names of the owner. The balance can be retrieved. It accepts deposit. It accepts withdrawals. And then the initial balance must be positive, and withdrawals cannot result in negative balances. Alright, so if I translate this English, there are multiple things that I would want to highlight at this point. Um, let's apply some of the rules of English grammar. I'm going to say that the green ones, they are nouns. So bank account here is a noun, right? So let's read it again. It has 10-digit number, right? When you specify a count like this, it is probably adjective, right? The green ones, so let's just say that blue is adjective, green is noun. We're going to have some verbs as well. So we're going to define verb in red, and there will be some noise. And then the noise we are going to define using the yellow color, and we're going to say that these are constraints. If you remember our class on databases, we had a similar color coding structure. So let's go ahead and start reading things. It has a 10-digit number, all right? So this is an adjective that uniquely identifies the bank account. Bank account is a noun, so we're going to save it here. It has a string that stores names or name or names of the owners, right? Owners, once again, is a noun, so I'm going to put a green color here. The balance can be retrieved. So balance is once again a noun, and then retrieved is a verb. So verb I'm going to use mark with red, and then it accepts deposit. So accept deposit is another verb. Accept withdrawal is another verb. The initial balance must be positive. This is a constraint, right? Must be positive. Make sense? And then withdrawals cannot result in negative balance. This is another constraint, right? If we take this thing and we apply the rule of abstract data type, we are going to come up with a new class. And instead of typing it in Visual Studio itself, I'm going to define it over here. You have multiple options over here. You can call it class, and you can call it struct, and probably you can call it record as well. Record is a new data type which got added in C# 9, I guess. Right? For our example, I'm going to restrict it to class itself. It is saying that there is a 10-digit number. Now for storing 10-digit number, you can get creative, but then I am going to leave it to integer, and I'm going to call it account number. Right? And then we are going to restrict it through different ways. We are going to save it in only 10-digit format. And then it is saying that it is identifying the bank account. So bank account itself is going to become the encompassing entity. Now I generally don't use underscores. I'm just using it for this example, but you don't use underscores either. And because I said that, let me go ahead and fix it. So I'm going to call it bank account. The account number, I'm going to leave it small letter, remove the underscore, and change the second letter um, to capital N. Then it is saying that it has a string and stores name or names of the owner. Over here, I want to point out to another type of constraint. So there is something called as a relationship, and then let's define relationship with the orange color. So it is saying that it has a string. Okay, when you see a sense of ownership with words like has, it is definitely indicating that it is going to become a member, right? And then we saw another example of has over here. It has a 10-digit number, right? And then because it is sharing a relationship with this noun bank account, they are all going to become member of the bank account. So let's go ahead and continue with our C# code. So we found out that account number has some sense of ownership, and then name of owners or name of single owner or multiple owner, it to me indicates that it is an array, and I'm going to call it owners probably because it is an array, right? And the next line is saying the balance can be retrieved. So balance itself, it also indicates it's an indirection. Has is not mentioned here, but then the account is going to have a balance. So let's go ahead and declare that. And because balance can be a floating point number, I'm going to use float, and I'm going to call it balance. Make sense? And then for the first time, it is talking about a verb. So verb is retrieved. So verb actually is a function, and function we are going to declare like this: void, and we're going to use present tense. Instead of retrieved, we're going to call it retrieve. And then probably you would also want to figure out the amount that can be retrieved. Make sense? Now it is saying that it accepts deposit. So let's go ahead and add those other functions as well. So void accept deposit, deposit of certain amount. So we're going to mention that amount here as well. And it is saying that the initial balance must be positive. So then I don't know if there is a U float. I'm hoping that there is. So we're going to change balance to an unsigned float so that it starts with at least 0, and after a withdrawal it never goes back to it never becomes less than 0. So withdrawal is also allowed. It accepts withdrawal, so I'm going to change it to accept withdrawal, and I'm going to say tell me an amount, and the initial balance must be positive, and then withdrawals cannot result in negative balances. All right, so I think we have an account class here, and then this class is built from this English like sentence. Right? You're going to receive requirements, or you will have to generate these requirements through the discussions that you are having with the potential users or sponsors of such projects. Once you read those requirements, your job is to apply the rule of English grammar and dissect your requirement into different consumable sections. And then each of these entities, they are going to either become the class name itself or the members, or they're going to become set of operations. Right? What we have essentially created using class is a new data type. Before this, the bank account data type itself, it was not present. What was present was primitive data types, integers and strings and booleans and things like that. We have, through this requirement, through the concept of abstract data type, we have come up with a new data type. It is going to store account number, the list of owners, the balance, and it is going to give you basic set of operations, just like integers, a 32-bit representation with 5 operations, all 5 arithmetic operations, right? So creating a class is not different than declaring an integer variable. It is just that you will have to think about the operations that you would want to support on that particular data type. Make sense? So moving on. Right. So let's go ahead and just copy this, go to our C# program and declare a class over here. And the bank account kind of fits right in, and it is complaining about uFloat. Probably float does not have an unsigned implementation. And then it is complaining about retrieve as well because it does not have a body. So let's go ahead and declare that body. I'm deleting the semicolon at the end with parentheses, which is saying that this is an empty function at the moment. So this works. I'll have to comment this out because characters do not support addition operation. Right. Um, the next concept that I would want to talk about is you can go ahead and start creating these objects, but using bank account, I'm going to say bank account, and this time you will have to use a new keyword. And then this is your first indicator that what is coming on the right is a reference data type. So with the new keyword, I'm going to say bank account. This is probably the last few times that you are seeing me type the new keyword in front of the class name that I have created. A warning with this new keyword that there are better ways of creating objects, and you should never put the new keyword in front of classes that you have written. Alright, this is a type of hard coding. Okay, but we're going to talk about that when we look at more advanced programming concept. So this bank account, on the bank account, I can say bank account dot, and not seeing anything. The reason I'm not seeing anything because there is something called as access specifiers, and the access specifier for all these 6 members, 3 data types and 3 functions, it is all private by default. If I want anything to be accessible outside, I'm going to have to use the public access specifier, or another equivalent of public is internal. So the internal is going to restrict it inside this particular namespace. So all the classes, all the functions that are inside the Hello C# namespace, only they will be able to access it. And then public, everybody anywhere who has this access to DLL, they will be able to call it. So we can create this member variable now. Now if I hit dot, it is going to show me all the members like account number, balance, and owners. And it is also going to show me the operations that are available on it. When you are writing advanced programs, you would want to hide fields like balance from the public access, and you are going to leave it private. But when you leave it private, you would want some form of control over how you how you modify it from the outside. And for that, you're going to have options of properties. And property is going to look a lot like this, but it is going to have a pair of getter and setter. So I'm going to pick this over here, and then notice that small letters here were fine, but then when you are exposing something to other people, other code, you would want to put it in capital letters. So there were 3 cases that we saw. This is the title case where each word has initial capital, right? This is called the title case, and the first letter is small, and the first letter of the next word is capital. It is called the camel case, and title case here. And then I have a programming practice where if I'm declaring a private variable, I generally start with an underscore. It saves me some typing. If I want to link these two, in the get block, I'm going to get rid of this, and I'm going to type return underscore balance like this. And inside set, I'm going to use underscore balance assigned to value. Right? Integer, and because it is float, it is completing. So let me change this balance to a float. Right? Notice that value is a keyword, and value matches to the type of this particular variable here. And this is how you can use getter and setter. This is not it. If you want to have some form of restrictions that value should not be 0, which was the constraint, you can put that constraint over here. If value is less than 0 point, because it is float, I'll have to probably put 0, 0, and I'm going to put a return statement, or I'm going to put another statement called throw new exception. An exception is a condition that you cannot handle at the moment, like um, balance cannot be less than 0, right? So we're going to talk about exceptions in the future, but then these were the constraints that we saw in our statement. The initial balance must be positive, and withdrawal cannot result in negative balance. So must be positive is like 0 or 0 and above. So we are checking exactly that, and when that doesn't happen, we complain, right? Right. So now I can come here and access the balance variable, and if I assign it say 10, okay, I'll have to put a 0 here. It is going to work fine. Precision float. I'm forgetting there's another keyword that you have to put here, probably M or F. Uh, okay, give me 1 second. Alright, there's an F that I have to put, and for there's another data type called decimal. For decimal, you can put an M there. Alright, so this is going to take a balance to 10, and now I can go ahead and print the bank account dot balance over here like this, and hit Control F5. And it's going to come and print this value for us as 10. So we have created a data type. We have the member variables inside it, and we are modifying each individual member. And we can also call some operations on it, like bank account dot withdrawal, accept withdrawal of say amount 5. And then now if I do bank account dot balance, and then for withdrawal, I'm going to come here and modify the balance value, assigned to balance minus amount, and it should work out. So it's going to print 10 first, and it's going to print 5 later, right? So 10 and 5 after withdrawing $5. What I wanted to showcase was that you have created a new data type. This data type has memory structure and it has operations, and then we are calling those operations and modifying this memory location or this memory structure that we have created. Another restriction that you can have on these data types is you might not want people to create object of this, because bank account is say the initial starting point, but then you would want to get more specific about what kind of bank account you want to get created. So if you want a saving bank account, right, or you cannot just say go and say that, hey, I want a saving bank account, because savings account is going to have a different requirement, different expectation from a bank account itself. And then that's when you start using the concept of inheritance. A saving account is a special implementation of the bank account. So I'm going to call it savings account, and I'm going to put a colon sign, and I'm going to inherit it from a bank account. Now when you put something on the right of this, it becomes the parent class, and this is the child class. And the parent class, if I don't want to have objects of this thing created, I'm going to put the abstract keyword over here. Now with the abstract keyword, it becomes an abstract noun, and it will not be possible to create object of this. And then if I scroll down now, it is complaining that cannot create an instance of an abstract type or interface bank account, right? So what it is essentially saying that this is an abstract class, and I can explain the concept of abstract classes to you, probably with an English example. When you say go to a market, when you are out in the market for looking for, let me just fix this first. It's a savings account, and it is complaining because it has become a subclass. I should have declared it outside the bank account class. Like this. Sorry. Alright, savings account is a class that is inheriting from the bank account, and now I'm able to create those accounts here. I'm going to replace, and okay, it is still completing, but let's go ahead and continue our discussion of abstract classes. Now, if you're in the market, you want to buy a car, you cannot just walk into a showroom and tell them that, hey, give me a car, right? They're going to definitely come and start asking you what car you want. And you will have to be very specific, and you will have to tell them probably you want a Maruti Swift, for example, right? What you've essentially done is you have moved away from an abstract class concept, and you have moved towards a specific concept. You cannot go to a vegetable vendor and tell them that give me vegetables, right? You will have to be very specific. That's the same thing that you can do with the fruit as well. And in the English concept, the English grammar concept that we are talking about here is the abstract noun versus the proper noun. Right? An abstract noun is car, a proper noun is probably Maruti Swift. Right? An abstract noun probably is fruit, a proper noun probably is apple. So when you are creating object, the reason you cannot create object of abstract class because abstract things will not give you anything. Right? But then if you look at an apple and you're like, hey, do you like having fruits? Right? And then the reverse transition is possible. So it's okay to call an apple a fruit and then ask for apple. Um, but then when you are referring to the fruit itself, you cannot say that, hey, give me a fruit. Right? You can get anything. When you want something, you will have to ask, be very specific. But then that very specific thing can be referred by its generic name because it is the relationship of abstract noun and proper noun in the English grammar. And then that grammar holds true in the C# programming language as well. When you are creating a class, if you put an abstract keyword, you will not be allowed to create an instance of this. You will have to definitely inherit them into something more specific. So suppose you have savings account, you have say a checking account that also inherits from bank account, and then if some of you have home loans, you can have a home loan account, you can have a car loan account. Like possibilities are like endless after this. And then each of these classes, they're going to have their own implementation. So a saving account can have an interest rate of say 10% in the entire year, and the checking account is going to have say 2%, right? A home loan is going to have 6%, 7%. So each specific account implementation is going to override some of the properties from the base account, and that is going to be the specific implementation, right? So these are uh, classes and abstract classes with members and functions. Right. So next, I want to talk about another concept called generics. So before we start, before we start that, let me just clean up a little. I'm going to start with a simple function called swap, and it is going to swap two values. It's going to take x and it's going to take the second number y. And at the end, I'm going to print the value of x like this, and I'm going to show you a new syntax with a dollar sign. If I put it in curly braces, it is going to print the value. So I'm going to repeat this for value y as well. I'm going to print y here. So what we are going to do is we're going to call this swap function, and it has to be static. I'm going to pass it value, say 10 and 20. Now when I call this function, no surprises, it is going to print 10 and 20 for x and y. What I want is, at the end of this function execution, I want these values to be swapped. And for that, I'm going to declare a new variable. Var is a way of declaring variable. I'm going to say temp. To temp, I'm going to assign x, and then y, and then y is assigned to temp. So the values of these two variables have changed. And just to verify, we're going to repeat this part here. Okay, now if I execute this, no surprises there. X has become 20 and y has become 10. Right? So let's jump out of this and let's try passing it to float variables. I'm typing a little f next to these numbers, and I've started seeing errors already. It is saying that I cannot convert from float to integer, right? And this is another concept of um, C# programming, that you can have two functions with the same name but different signature, right? And the signature starts after the function name. So anything on the left of the signature does not count. So I'm going to put a float here and I'm going to put a float here, and notice that the error has kind of disappeared. So it now knows that it has to go inside this function, and just because we are inside float, I'm going to put a hard-coded string float here. Now if I run this, we are executing the float variant of the swap function. It took 2, 10, and 20, and then it swapped the variable x and y. Now, every time, my professional tip to you for today, every time you do a copy and paste, you should really take a pause and you should think about, is there anything that you are doing wrong because you just copied and pasted something, right? So copy paste is a terrible operation and it should make you stop and think about your solution one more time, right? There is a concept. So we first saw the concept of polymorphism, having two functions with the same name and different set of data types. It is going to work, but I don't want this, right? I'm going to use another concept, and it is called as generics. So in generics, I'm going to take the function name and I'm going to say that I'm going to modify the way we define functions, and I'm going to put angle brackets right next to it, and I'm going to put a type here. I'm going to call it t, and I'm going to replace x with integer with t, and um, this second integer also with t. What it is essentially saying is that regardless of what data type is coming in, just go ahead and accept it, right? It's a float, so I'm going to take the float value. If I pass it, say, a character value, right, it is still going to work. So with one implementation, we have removed the type and we have told it that whatever type is coming in, just accept that type, right? Now, if I execute this code, it's going to look very funny. That x was x first, y was y first, but then after the swap, x became y and y became x. It doesn't care about the data type that you are going to pass to it. It is just going to work. It's going to work for 10 and 20, it is going to work for 10 of float and 20 of float. But here's the thing, if I pass a character here and a float here, I think they should give me some compile error. So, alright, probably a good example. 97. Do you remember where this 97 is coming from? So this is the ASCII code of small letter a. The compiler has gone ahead and it has bumped up the type of this character and converted it to an integer. But in cases where it cannot make that transition from one type to another, it is going to complain. So if I change it to 20.5, I think it is going to bump this up from an integer to a float once again. So let's go ahead and change this to hello, right? And now it is complaining. And look at the error message. The argument for the method, it cannot be inferred from the usage because this is string and this is a floating point number. We cannot jump between these two types. And then that's what it is saying, that I was expecting only one type, but then I got like two types. And in these two types, they probably cannot be interchanged, right? And this is in summary generics for you. So all you have to do is you have to identify the type, and then you can go on replacing these type with their generic equivalent, and these equivalents then will have to be mentioned alongside the function name. But then generics can also be available at the class level. And if I'm declaring, say, a bank account, I can put a T over here, and then I can start using T as a type here. So T account number, for example. All right. So my account number can be integer, it can be float. Make sense? So generic gives you that flexibility of data type, of how you would want to perform, how you would want to replace or leverage different data types with only one set of declaration. So we're going to see a lot more generics in our next upcoming sections, and then it's going to become more clear as we work more on this. All right.